My screen visible to you?
Yes, sir.
Okay. Please answer your attendance. Aditya Kumar. Aditya Kumar.
Come in, ask him to come in, sir. Sir, he will come, sir.
Just tell him one.
But currently he is yet to join, right?
Right, sir.
Okay. Anand?
Yes, sir.
Anand Kumar?
Yes, sir.
Arnachalam?
Yes, sir.
Vasan? Vasan?
Present, sir.
Hemant?
Present, sir.
Jagan?
Yes, sir.
Kesav Prasad? Kesav Prasad?
Sir, he's raising the hand. I think he's having mic issues.
Okay, he's having problem with the mic. Okay. Lakshmi Narayanan?
Sir.
Prabhakaran?
Present, sir.
Prem Vinayak?
Present, sir.
Rahul?
Present, sir.
Roshan Kumar?
Yes, sir. Present.
Sabish Kumar?
Present, sir.
Satish Kumar?
Present, sir.
Titus?
Present, sir.
Valish?
Yes, sir.
Vigneshwaran?
Present, sir.
Vijay
Present, sir.
Vikash?
Present, sir.
Vivekanand?
Present, sir.
Yadav?
Present, sir.
Yuvraj?
Present, sir.
Sir, Aditya reached.
Sir. Aditya is present?
Yes, sir.
Okay, fine. Perfect. So all are present today.
Okay.
Okay, so welcome back to this course on IC engine combustion pollution. We are in chapter 1. Here we are discussing role of fuel in engine combustion. So far in this, we discuss role of fuel in engine combustion. I have chosen diesel engine combustion, and we have seen what role is played by the fuel in influencing the combustion process. Right, and then in the previous class, we discussed about the criteria used to select fuel for automotive engine application. So we have seen that 99% of the demand for the automotive sector is met with only liquid fuel. Gaseous fuels have only 1% share out of the total fuel requirement. Only 1% of the transport or automotive sector is met with gaseous fuel. So here we discuss some of the limitations or shortcomings of gaseous fuel. Because of that, its current share is only 1%, although today we talk a lot about using gaseous fuel in IC engine. Different countries are promoting that hydrogen, especially hydrogen and ammonia. There's a lot of work going on. They want to use this fuel primarily from the perspective of eliminating carbon-based emission. Hydrogen and ammonia are carbonless fuel. So government promote utilizing carbonless fuel because of the pressure, political pressure to reduce carbon-based emission due to the contribution in the global warming. We have recently witnessed a drastic change in the seasonal rainfall pattern and other effects. So one of the reason is the average Earth's temperature is increasing due to the global warming effect, and so all sectors are tightened up to reduce carbon-based emission. So there's a lot of incentives, I would say, to promote. The government of India has also set up a large project for producing hydrogen, right? Green hydrogen, they say, from renewable source. But currently it is not yet feasible. The technology is not yet feasible. We discussed shortcomings of using gaseous fuel. Liquid fuels are being used now almost 100 years. And out of this 99% demand for the transport sector met with liquid fuel, 95% is met with fuel produced from crude oil. Right, crude oil, gasoline for spark ignited engine and diesel for compression ignited engine. They meet the 95% demand currently, and these two fuels are being used for a longer period of time because of the characteristic of these fuel, which makes them unreplaceable. One of the major reasons, as we discussed, is the volumetric energy content is very high, which is uncomparable with gaseous fuel. They have very poor volumetric energy content. So the system is compact. Compactness is one of the major requirement, right, for automotive or any transport or mobility application. So we want high power to weight ratio. We want to reduce the weight, and we want the system as compact as possible, occupying less space. So from the fuel perspective, the fuel should possess high volumetric energy content. That's what this liquid fuel made from crude oil have. And the fuels are also safe because we store, transport these fuels under ambient pressure conditions. For gaseous fuel, we need to pressurize to a higher pressure value. I said I've given some typical number. For natural gas, it's around 200, 300 bar, and for hydrogen, it should go up to 700, 800 bar because of the changes in the volumetric energy content. And I have also discussed some of the problems, associated problem in compressing and storing hydrogen-like fuel at such a higher pressure. So having understood that we primarily use gasoline in SI engine and diesel in CI engine, we want to understand the molecular composition and molecular structure of this fuel. So before that, we need to track the origin of the fuel because the source of the fuel will decide its composition. From that perspective, we have discussed in the previous class how gasoline and diesel are produced from crude oil, which is a source for producing this gasoline and diesel. Unfortunately, we do not have a large crude oil reserve in India, so we import this crude oil from other country, primarily Gulf country, right? And then we process this crude oil to get gasoline and diesel. So we have a lot of refineries in India, private run refineries and government run refineries. And these refineries process the crude oil and produce gasoline and diesel with the required well-defined specifications, right? Like emission specifications, we also have fuel specifications in different countries. In India, we have our own IS standard. So the fuel legally sold in the market has to comply with the specification. So the major task for the refinery is they have to produce gasoline and diesel with a well-laid, the specification should be met. Currently, we are using BS6 fuel, and norms, emission norms are also BS6. So there are fuel quality requirement that needs to be met. That is what we have seen, that our refineries are producing the fuel with the required quality. The current, having understood that we have obtained gasoline and diesel from crude oil, now in this class, I'm going to discuss about this molecular composition and molecular structure of hydrocarbons present in gasoline and diesel. So gasoline and diesel, they are primarily designated as hydrocarbon fuel because the major elements or atoms present in gasoline and diesel composition is carbon and hydrogen. Carbon typically up to 84%. Hydrogen is around 14%. 2% are other trace elements. Okay, of course, in the current fuel specification, we restrict the sulfur content to very low value. We call it as ultra low sulfur. Sulfur in gasoline is negligible. In diesel, it's relatively high, but nevertheless, we use a very low sulfur content. Apart from that, you may have slight little bit of nitrogen and oxygen, right? So those are called trace elements. So you have some trace elements apart from carbon and hydrogen. Carbon and hydrogen are the major elements present in gasoline and diesel. That's why they are referred to as hydrocarbon fuels. Hydrogen and carbon are the major constituents. So what we have understood is this gasoline and diesel are complex multi-component mixture of hydrocarbon. Complex multi-component mixture of hydrocarbon. Why I say it's a complex mixture, complex multi-component mixture? Because because from the analytical techniques, in fact, it's not one technique that we can use to identify what is inside gasoline and diesel. We have to use multiple analytical techniques to identify the composition of gasoline and diesel. Although we use this two fuel in our day-to-day life, we never pay attention to the composition of this two fuel, which is very important to know from the perspective of understanding the combustion process undergone by this fuel. That's why we are spending time to know about this. So as I said, we have to use multiple analytical technique because the number of hydrocarbon present in gasoline and diesel can vary anywhere between 100 to 1000. You can now imagine the complexity of the fuel. We have around 100 to 1000 different hydrocarbon present in gasoline and diesel. Okay, so why it is given in range? Why it is not a specific number? It is provided in range. What could be the possible reason?
Molecular bond, sir.
What is that molecular bond?
What I mean to say is like ethanol is there, then C2H5, then benzene can be S6, C6S6 like that.
No. My question is not about molecular structure. My question is why it is given in a range. Why it is not a fixed number, rather it is a range.
Maybe outputs of different stages of refining, like gives different quality or something like that.
Okay, and the refinery process, you are saying that this
No, yeah, at different stages we get different levels of purity and so on.
No, that's fine. We are not talking about.
Sir,
we are not talking about getting fuel at different stages. We have a final. We are talking about the final gasoline and diesel output from the refinery, which will be in the form of range.
Okay.
Sir, based on analytical technique, it can have different basically sampling, and because of which there might be range. Because the different analytical technique might give some different number of.
Okay. Anything else you can think of?
From boiling temperature perspective, if you see different,
that is fine. That is different
hydrocarbons
for gasoline and diesel. That is fine. Anything else?
Sir,
Yeah.
if we say it a diesel, like there are different composition that we accept in that criteria, that whether it is a diesel or petrol, there are different compositions and different combinations of molecular structures that makes the diesel or petrol. So that may be the reason that we give that range, that if it is in this range, this is accepted as diesel. If the compositions are in this range, this is accepted as petrol.
No, that's fine. For gasoline and diesel, you have different hydrocarbon. That is fine.
Yes.
But this is a rough number I have given. This rough number is not one value, rather it is a range. This is primarily because of differences in the crude oil source. You should always remember that remember the source from which gasoline and diesel are produced. So the source is crude oil, as we have discussed in the previous class. Okay, so crude oil is what is being given as an input to get gasoline and diesel. Of course, jet fuels are used in aircraft. We are not going to discuss about that. So in the previous class, we discussed that the refineries carry out various processes. I have summarized these processes also to get into gasoline and diesel. See that the problem is this crude oil itself is a multi-component mixture. It's a hydrocarbon. That's why you are finally getting gasoline and diesel as a hydrocarbon mixture. Okay, the number varies because the source itself is a variable. Any multi-component fuel compared to single component fuel, the problem with multi-component fuel is very difficult to maintain identical composition because the source itself is going to be different in different parts of the world. Recently, if you remember, we obtained crude oil from Russia. Earlier, we generally get most of the crude oil from Gulf countries. You may be knowing that. Okay. And you know that the price of gasoline and diesel, now it is out of control of government. It has allowed the refineries to fix the price. So every day it will change. Recently it has stabilized, but earlier you would have noticed that every day it is going to be different because the source price is not decided by us. It is decided by some other country. Unfortunately, we don't have a reserve, we import. So we are not fixing the price of crude oil. Okay, it's fixed by some other country. Based on the source price, the price of gasoline and diesel was different. Okay, so every day it was changing, right? So it's a kind of affecting the economy because kind of fluctuating price, and we use heavily these two fuel, right? So the economy itself was kind of fluctuating, unstabilized, primarily because we don't have the reserve. The point here for you is this gasoline and diesel hydrocarbons are given in range because the crude oil reserve in different parts of the world are different. The crude oil available in Russia is going to be different from the crude oil available in Gulf countries. The crude oil available in US is different from the crude oil available in Europe. Later on, I will show some interesting results about the effect of this variation in the crude oil reserve and the associated variation in the properties of gasoline and diesel. Okay, so it is given in range. The hydrocarbons are given in range because the source itself is subjected to variability. The crude oil that we get from different parts of the world are going to be different. Accordingly, the number of hydrocarbons in gasoline and diesel are going to be different. So one of the most widely used analytical technique you might have come across, GCMS, gas chromatograph with mass spectrometry. It's one of the analytical technique. As I said, we need to use multiple techniques because it's a complex mixture. Multiple techniques only can reveal what is inside this gasoline and diesel in terms of its composition, right? That is point number one. And second one, based on from where you get crude oil, right? The composition of the gasoline and diesel is going to be different, right? Now,
Sir, sorry, sir. GEMS, what is the full form you told, sir?
gas chromatography with mass spectrometry. This is one of the analytical techniques used to identify the composition, molecular composition of a fuel. Okay.
Thank you, sir.
So now the question is, we do a lot of numerical simulation also, right? We simulate the combustion process of SI engine and CA engine. I don't know, maybe some of you might have been involved in that. So this simulation of combustion, right? One of the important information you need to know is about the fuel. Now I'm saying that this fuel is a mixture of 100 to 1000 different hydrocarbon. Can we include all this hydrocarbon in your numerical tool? Whatever numerical tool, there are different numerical tools, CFD tools being used to simulate the combustion process, right? We definitely need to include fuel and its composition in the code to capture the effect of fuel in the combustion process, which is playing a primary role in the combustion. Now, how do we include all this hydrocarbon in any numerical tool? Is it possible?
No, sir, it will be very difficult.
We cannot, right? The code will crash. Any numerical CFD code will crash if we include all this hydrocarbon to represent the fuel, gasoline and diesel fuel, right? So it's impossible task. So then how we are carrying out the combustion simulation?
Sir, we have to use standard fuel.
We have to use a standard fuel. What do you mean by standard fuel?
Based on most prevalent.
For our testing, we use a standard like known value octane fuel that we are using. So that value can be, the value of that can be asserted in the code in that sense.
No, I'm not talking about the value or property. I am talking about the fuel. So when I say fuel, you have to include its composition, right? Only if composition is included, property will come after that. Property is dependent on the composition. So my question is, how do we define the composition? Because I have a complex hydrocarbon mixture, which has around 100 to 1000 different hydrocarbon. Just now I said that I cannot include all this hydrocarbon, otherwise the code will crash. It cannot handle. Any numerical CFD tool cannot handle such a complex mixture of hydrocarbon. But we do carry out the simulation work, combustion simulation work, right? It's one of the routine work. I think in your industry also, there is a separate CFD team taking care of simulating the combustion process because it's an integral part of engine design and development. Without CFD, you cannot develop a new engine or a new concept.
So can we categorize it based on the geography?
Geography, yeah, again, based on the geography, what I'm saying is this number only will vary. It can be anywhere between 100 to 1000. It's given in a range. Based on the geography, it's going to be different. But
Sir,
we cannot include all this. So how do we carry out simulation work in such a case?
Maybe some weighted equivalence, like generally we talk about this Pareto and all, right? Like the 20% of content is what results to 80% of effect, something like that. So this 20% hydrocarbons is common across all variants. So we take that as a starting point for our simulation, something like that. Which is most prevalent across regions and so on.
No. I think you are talking about optimization. 2080 is a split for calibration and validation.
In my opinion, so it should be some standard value of what I mean to say is like ideal fuel, you can say in that way, like which octane is 100 in that way.
Sir, could it be whatever maybe the number of compositions, the carbon percentage and hydrogen percentage are known relatively. So that can be taken as an input, standard input, and
yeah. So carbon and hydrogen should be known to you. In fact, you need to know the chemical kinetic mechanism. I'm going to briefly talk about chemical kinetic in the 4th chapter. Okay, so that is important. Kinetics are important. Kinetics depends on the composition. So fortunately, one important aspect that you need to take away here is this 1000 different hydrocarbon can be binned or grouped into 5 classes. What I mean to say is this 1000 will collapse into 5. Based on what? Based on similarity in molecular structure. Although I have 1000 different hydrocarbon, they have only 5 distinct molecular structure. Okay, so based on differences in the molecular structure, we can categorize these 1000 different hydrocarbon into 5 classes. It is called hydrocarbon classes. So we can group them into 5 classes. What are those 5 hydrocarbon classes? One is normal paraffin, then isoparaffin, cycloparaffin, olefin, and aromatics. So these 5 are called hydrocarbon classes. So you can group these 1000 hydrocarbons into 5 classes as indicated here. Okay, so this grouping is done based on similarity in the molecular structure, right? This is very fortunate because what I will do is when I want to simulate the combustion process with gasoline or diesel, I will consider only these classes, 5 classes. I will take 1 or 2 representative hydrocarbon for each class and then carry out the simulation. That is how the combustion simulation is being carried out now. You may be surprised to know that most of the time we use only 1 hydrocarbon to mimic or capture the characteristic of 1000 hydrocarbon. It is a surprising thing, right? But that is a very simplified assumption. You have to go for more than 1 hydrocarbon, but you have to carefully choose those hydrocarbon, because remember that with those very few hydrocarbon, you have to capture the characteristic of 1000 hydrocarbon. Okay, so it is a challenge, right? How many, what kind of hydrocarbon you choose to carry out your combustion simulation is an area by itself. It's a challenging task. So this approach is called surrogate modeling approach. That is the approach being currently used to carry out combustion simulation of SI engine and CA engine with gasoline or diesel, right? Surrogate is a representative hydrocarbon. We use only very few. The most simplified case is you use only 1 hydrocarbon to capture the characteristic of 1000 hydrocarbon. Okay, this is an important point to note down. As I said, this 1000 is grouped into 5 based on this consideration. They have only 5 different molecular structure, these hydrocarbons. What are they? As I said, normal paraffin, which is having a chain-like molecular structure without any double bond. Then you have olefin class. Again, it is like a chain-like structure with double bond, right? The difference is here in this case, you have a double bond present in the molecular structure. You have isoparaffin. In this case, you have a branch, not chain. It's a branch molecular structure. Then you have cycloparaffin. It is a ring-like molecular structure, not branch, it's a ring, but without double bond. Then you have aromatics, ring-like structure with double bond. Ring-like structure with double bond, okay? So all these are hydrocarbon. I will show the typical structure, molecular structure of these 5 classes. But before that, just take a note that from the perspective of connecting carbon and hydrogen, carbon is a tetravalent, meaning it needs 4 bonds to get connected to another carbon atom. Carbon needs 4 bonds to get connected to another carbon atom or hydrogen atom. Okay, so but these 4 atoms can be anything. I have shown 3 cases, 3 possible cases here. All the 4 are single bond. Case number 1. Case number 2, you have 2 single bond, 1 double bond. Case number 3, you have 2 double bond. So this tetravalency is satisfied in all the 3 cases. But in case 1, you have only single bond. Case 2, you have a double bond, 2 single bond. Case 3, you have 2 double bond. Whenever you have a double bond, it is said to be an unsaturated hydrocarbon. These 2 are unsaturated hydrocarbon. Whenever you have all single bond, it is said to be a saturated hydrocarbon. This is very important to know. There is a bit of chemistry involved here. This is important to know because how carbon and hydrogen are connected in a hydrocarbon fuel carries a lot of significance because the energy that you need to form a radical from a single bond is different from energy you need to provide to form a double bond. Please note, earlier we discussed about radical formation, right? So fuel possesses chemical energy in the form of enthalpy of formation. What we do in a SI engine and CI engine combustion, to initiate SI engine combustion, we discharge electric spark. What this spark discharge do? It provides thermal energy or activation energy to form radical. I have already said about this. In a diesel engine, you are compressing air to a high pressure and then later on you are injecting fuel. So this compressed air is providing activation energy to break the fuel molecule and form bond, and form radical. Once the radicals are formed, the combustion event gets started. And I already told you that the combustion event is a self-sustaining event. It will go on its own as long as sufficient radicals are available. Right? You have to just initiate. To start the combustion event, you are providing spark discharge in SI engine. In diesel engine, you are compressing to a high pressure, high temperature. This helps in initiating radical formation. Once the radicals are formed, the reaction go on its own. Until sufficient radicals are available, the combustion event will continue to happen and thermal energy release will continue to happen. Okay, so this is what is happening, and the energy that you provide depends on 2 things. Whether you have a single bond or a double bond, it also depends on how the carbon and hydrogen are connected. This is where molecular structure comes into picture. The way the carbon and hydrogen are connected and the number of bonds present between carbon and hydrogen is going to decide the activation energy that you need to provide to initiate combustion. Okay, so molecular structure shows how the carbon and hydrogen are connected. It will have a significant effect on ignition quality of the fuel, which is measured in terms of cetane number. It is going to significantly affect antenna quality, measured in terms of octane number of gasoline. Cetane number is required for diesel. We have already seen that these 2 are inversely proportional. The way the carbon and hydrogen are connected is going to be affecting the ignition quality and antenna quality. Now with this background information, now I will show the schematic of these 5 different hydrocarbon classes. So these 5 are the hydrocarbon classes, right? So we have this 1000 hydrocarbon, and this 1000 hydrocarbons in gasoline and diesel can be grouped into these 5 classes. You have only these 5 different molecular structure in the case of hydrocarbon present in gasoline and diesel. So the first one is normal paraffin. You could see that it is a chain-like structure. Carbon and hydrogen are connected with a chain-like structure. This is without any double bond. So it is a saturated hydrocarbon. Now you look at the olefin hydrocarbon class. Again, same chain-like structure. But what is the difference you are noticing here?
They double bond.
It has a double bond. Okay, here all are single bond. With carbon, you have all 4 single bond. As I said, 4 bonds, all the 4 are single. Now you look at this 2 carbon. In this carbon, you have a double bond, you have 2 single bond. So even if 1 double bond is present, it's said to be unsaturated. This is isoparaffin class. You have a branched structure. It's not chain, rather it's a branch structure. To the second carbon atom, there are 2 methyl groups attached. CH3 is methyl group. So you could see one CH3 group here, another CH3 group here. Two CH3 groups are attached to the second carbon atom. To the fourth carbon atom, one more CH3 group, methyl group is attached. So you have branching because of attaching the CH3 group to the base structure. This is a base structure. Then you have branching because of fixing the CH3 or methyl group to the second and fourth carbon atom. You look at the cycloparaffin class, it's a ring. It's a ring-like structure. This is without any double bond. Then you have aromatics. This is also a ring, but with a double bond. Okay, so you have this 5 distinct molecular structure, and based on that, we have 5 classes. What is also given here is one of the hydrocarbon present in the particular class. So you have normal paraffin class. N-octane is one of the hydrocarbon present in this class. Cn is cetane number. Cetane number of this particular hydrocarbon I have given. This is just to visualize how the cetane number or ignition quality is going to be different based on differences in the molecular structure. Okay, so I have given 5 classes, one example hydrocarbon for each class. I have also given cetane number of that particular hydrocarbon. Okay, to see how the molecular structure affects the ignition quality measured in terms of cetane number. Okay, so now with this background information, you just look at how the cetane number is varying. So for normal paraffin, it is 64. For olefin, you could see that it is 41. N-octane and 1-octane. Okay, so these two hydrocarbons are having same number of carbon atom. You could count the number of carbon atom in these two. They are having same number of carbon atom, but you see that the ignition quality drops in terms of cetane number value from 64 to 41. Can you tell me the possible reason for this?
So activation energy required to break the double bond is more compared to single bond.
Yes. So there is something called bond energy. The energy that you need to provide to break the bond depends on the number of bond. When you have a double bond, you have to provide more energy to break and form radical. So because of that, your ignition quality drops. Ignition quality is a measure of how quickly you can form radical from a molecular structure. Okay, if you can quickly form a radical, then ignition quality is better. If you have to provide more energy to form radical, then the ignition quality is accordingly can be categorized as poor. So there is something called better ignition quality, poor ignition quality. Okay, better ignition quality is defined if you can readily form radical, easily form radical. Poor ignition quality is defined when you have to provide more energy to form radical. Okay, so this is understandable between this N-octane and 1-octane. One is normal paraffin class, this is olefin class. Here you have a double bond, so you have to provide more energy to form radical. That's why the cetane number drops from 64 to 41. Now you can look at isoparaffin. It's a branched structure. It's more stable compared to chain structure because of the. Yeah, you asked something. Okay. Because of the branching, you could see the cetane number, change in cetane number. Instead of 64, it is now dropped to 12. Ignition quality.
Yeah.
Hello.
Sir, here it is. Sir, can you audible, sir?
Yes, audible.
Okay. Sir, here further it is reduced to 12. Here there is no double bond is there, right?
Here there is no double bond, but the structure, molecular structure is stable. If you have a chain-like structure, it's easy to initiate radical formation. But if you have a branching in the structure, it is somewhat stable molecular structure. So radical formation is taking more time, or you have to provide more energy for radical formation because somewhat a stable structure. Now you look at the ring. Ring structure is also stable, so cetane number is 22. Ring with a double bond is the most stable molecular structure. Cetane number is 0. Cetane number is 0 for benzene, which is one of the hydrocarbon present in aromatics. Okay, this is the most stable molecular structure. It is also having a double bond. So there are two things that are affecting here. One, whether it is a single bond or a double bond. Second one, what kind of molecular structure. Branched structure and ring structure are stable. Chain structure is somewhat unstable. So you can initiate radical formation quickly. Whereas these structures are stable, so it needs more energy to initiate radical formation. In this kind of structure, if you have a double bond, it's going to be much more stable. Okay, that's the physical meaning of this. Did you get?
Yes, sir.
So now you understood that.
Sir, 1 minute.
So one doubt, sir, in cycloparaffin structure, is
Mhm.
it having both sides double bond with the hydrogen?
No, this is only single bond. It doesn't have any double bond. It doesn't have any double bond. It has only single bond.
Sir, one doubt.
Yeah.
Sir, this process only we are calling as additive mixing process. Sir.
Additive?
Additive mixing process in diesel after extruded from crude oil. In diesel, some additives they will add, no, sir, to get different
No,
properties.
additive is a different thing. So here I am showing the effect of molecular structure on the ignition quality. Okay, additives are is an area by itself. There are different additives. Additives are mean for achieving a target property. Each and every additive that is designed will have a target property. For example, if you take ethyl exyl nitrate, it is one of the ignition improver additive. So these additives you use in ppm level, very small quantity, but they are designed to provide a target function. EHEN in ppm level, it will improve the ignition quality that will reflect in C10 number. For increasing C10 number by 5, there is a finite or fixed level, ppm level of EHEN you need to add. So each additive will achieve only its intended target function.
So this different C10 number is there, no, say 64, 22. This will impact in emission also, sir. If we are using this.
Exactly. This is going to affect everything. Later on, we will discuss about that. Okay. This is one of the important things that you need to understand. We have hydrocarbon with these 5 different molecular structure. Based on the type of molecular structure, ignition quality is different. I already said that the ignition quality and antenna quality are inversely proportional. When I say fuel has a high CT number, it means it has a very low octane number. That's why a good fuel for diesel engine application cannot be a good fuel for gasoline. Meaning, you cannot use gasoline in diesel engine, you cannot use diesel in SI engine. Okay, the fundamental ignition requirements are totally different in these 2 IC engines.
Okay.
Clear?
Thank you. Thank you. Yes, sir.
So
when we say C10 number is 0, that means this fuel will not be
igniting under normal conditions. So you need to use some additive to make it.
Right. Okay.
Okay.
Thank you, sir.
So later on, I will discuss about how the C10 and octane numbers are measured. Okay, there you will get more idea about these numbers. Okay, but here our objective is to understand the effect of variation in molecular structure on the ignition quality. So when I say ignition quality is better, it means antenna quality is poor. Meaning normal paraffin will have a poor antenna quality. Aromatics will have a better antenna quality. Clear?
Yes, sir.
Yes.
So you have these 5 different structures and they have a significant effect on ignition quality. Now with this understanding, you will be able to tell now what kind of hydrocarbon class is required for diesel combustion, what kind of hydrocarbon class is required for gasoline combustion. So what do you need for CI engine application? What kind of hydrocarbon?
Paraffin.
You primarily need this kind of chain-like structure, paraffin mostly, right? Because this is having better ignition quality. To avoid knocking combustion, you need such a hydrocarbon in large proportion for diesel in its molecular composition. And for gasoline you should avoid this, right? If you use this, what will happen in SI engine?
It knocks.
High knock. Okay, so it's going to knock. Engine is going to knock. So you have to avoid such hydrocarbons in gasoline. So what kind of hydrocarbons you need for gasoline combustion?
Aromatics.
Benzene or ring like this.
More aromatic, more cycloparaffin, more isoparaffin and olefin. So you need this kind of hydrocarbon to be included in gasoline. You need these kind of hydrocarbon to be included in diesel. This is what you are seeing here. This is a molecular composition of gasoline and diesel. There are 2 things here. One is a plot which shows carbon number distribution of hydrocarbons in gasoline. It is from C3 to C13. That is a carbon number distribution. And there are two different variants of gasoline. That's what these two lines are. You ignore that, but the takeaway for you is to look at the carbon number distribution in gasoline, C3 to C13. And most of the hydrocarbons peak values are around C5 to C8. Most of the hydrocarbons are with the carbon number 5 to carbon number 8. Okay, so the molecular mean or average molecular weight of gasoline is 110. You have C3 to C13 hydrocarbon. That is why it is classified as light distillate. Meaning you have a low molecular weight hydrocarbon. If molecular weight is low, what will happen to boiling temperature?
It will decrease, sir, lower.
Lower. So I can say that it is a high volatility fuel. This is what I said earlier, right? It's a light distillate, high volatility fuel. This is one of the important requirement for SI engine application. You need fuel with a high volatility, meaning you need fuel with a low molecular weight hydrocarbon that should boil quickly. Can anyone tell me from your understanding of SI engine mixture preparation, why you need such a high volatility fuel for SI engine?
For the flame propagation, sir.
For
If you don't have the
To have a homogeneous mixture of
mixture and flame propagation file.
you have to prepare a homogeneous fuel air mixture for spark ignited engine, otherwise it will be a problem. Perfect. Anything else?
Sir,
When do you introduce fuel in a typical spark ignited engine? In engine operating cycle, when do you introduce fuel or inject fuel in a spark ignited engine?
During the suction stroke.
Suction stroke. And during suction stroke, where do you introduce fuel? In the intake port, right?
Yeah.
What is the
Yes.
typical pressure?
Sir, it should be 20.
200,
200.
No, not 200, sir. It's a 20-30 bar max in that way.
20-30 bar.
4 bar.
No, sir.
4 bar.
6 bars. 6 bars.
Typical
Sir, it's
pressure.
a section stroke. It's
I think
basically
20.
4 bar.
4 bar.
Typical pressure is around 3 to 5 bar. So you are injecting gasoline at this condition, 3 to 5 bar. Temperature is ambient temperature. So you have a very low pressure, very low temperature. This is how you introduce fuel, gasoline into spark ignited engine during the suction stroke or intake stroke. So you are not providing any external aid to vaporize the fuel. The fuel has to vaporize by itself. Fuel has to vaporize by itself. Okay, because the conditions are not conducive for vaporization. It's the pressure is low, temperature is low. The fuel has to vaporize by itself. That's why this is one of the important requirement for SI engine application. You need to have fuel with a high volatility so that it can vaporize readily. It can mix with air and form a homogeneous mixture, as some of you highlighted. You need to form a homogeneous mixture. We cannot form a heterogeneous mixture in SI engine. It will lead to various problems, including high emissions, polluted emissions. So we need to form a homogeneous mixture. We are not providing any external aid for fuel vaporization because pressure and temperature are low. The fuel has to vaporize by itself. That's why this is one of the important requirement for gasoline. It needs to be highly volatile. It should readily vaporize, mix with air quickly within the limited time. See, all this are happening in millisecond time scale, millisecond or microsecond time scale based on the engine running speed. So this has to happen as quickly as possible. So I would say that one of the fundamental requirement for SI engine application is the gasoline fuel should have a high volatility. Okay, that's why its carbon distribution is from C3. C3 is very low, right? Less number of carbon. That's why the fuel could quickly vaporize, mix with air. Okay, and now in the bottom you have a table. The table shows the hydrocarbon class distribution in gasoline. Molecular composition is provided here in terms of hydrocarbon class. Percentage mass of this different hydrocarbon classes are provided here. But the takeaway for you is isoparaffin, you see the percentage mass 31.1%, olefin 18.7%, aromatics 35.5%. So these three classes, isoparaffin, aromatic and olefin, these three put together, you have more than 80%. More than 80% of gasoline composition comes from these three hydrocarbon classes, isoparaffin, olefin, aromatics. Why? Because they have poor ignition quality, meaning they have a better antenna quality. Okay, so I use the word reactivity. Because of this composition, gasoline has a low reactivity, or in other words, it has a better antenna quality, so that you can avoid knocking combustion when you apply this gasoline fuel in a SI engine. So this is a second important information you need to take down based on the molecular composition and molecular structure information of hydrocarbon present in gasoline. Gasoline is a high volatile fuel, it's a low reactive fuel, so that it has a better antenna quality, it resists knocking. Okay, so accordingly, our refineries have tuned the molecular composition of gasoline in terms of stable structure, molecular structure, so that the fuel resists ignition. This is what I mean by low reactivity. Fuel resists ignition, so that its antenna quality measured in terms of octane number is high. Okay, so the engine runs smoothly with less combustion noise. Okay, that is what we prefer for spark ignited engine application. Now you look at diesel, which is present on the right hand side. Look at the carbon number distribution. It starts from C9, it goes up to C23. C9 to C23 is a typical carbon number distribution. The maximum contribution comes here from C14 to C18. C14 to C18 carbon number is present in maximum proportion in the diesel, right? So its typical molecular weight, average molecular weight is 195. That is why it is categorized as heavy distillate. So it's a heavy distillate fuel, meaning its molecular weight is high. It's a heavier fuel. Boiling point is high. That's why it is called heavy distillate. So I can say that this fuel has a low volatility because of this carbon number distribution. Can someone tell me, is it not a problem in a diesel engine or CI engine when you use diesel with such a low volatility or high boiling range? Boiling range we have already discussed previously. So it is from 160 to 380. For gasoline, it is 20 to 200 degrees Celsius. So this is a heavy distillate, right? Heavy hydrocarbon present in diesel that increases the boiling temperature, 160 to 380. Now, does it affect CI engine performance? Is because it resists vaporization, right? In a diesel engine also, when you introduce fuel, it's going to resist vaporization because of its low volatility. Does it cause any problem in a CI engine?
But in the CI engine, the fuel is injected only in the compression stroke. So already the temperature and pressure will be higher. So
exactly,
that's the reason why it's this.
Exactly. This is a perfect reason. So you inject fuel at high pressure, and when do you inject? Here you are injecting fuel in the pore during intake stroke. In a diesel engine, CI engine, you inject fuel during compression stroke, later part of compression stroke. And you inject fuel at a very high pressure, right? So pressure anywhere between 300 bar to 3000 bar. I already discussed about this when we discussed about fuel effect in the first part of this course. 300 to 3000, very high pressure. It helps in quicker atomization. Inside the cylinder, you have air at high pressure and high temperature because compression ratio is high. So although the fuel has a low volatility, it doesn't matter in a CI engine because you are injecting fuel at high pressure, and what you have inside the cylinder at the time of injection, fuel injection, is you have a high pressure, high temperature air. So you have favorable external conditions in diesel engine to vaporize the fuel, although you have a low volatile fuel which resists vaporization. Resist means it will delay the vaporization event, but your conditions are favorable to quickly vaporize. Again, this should happen in micro or millisecond or nanosecond time scale based on the diesel engine running speed. Okay, it needs to be happening very quickly. Although you have a limitation from the fuel property perspective, it is taken care due to better conditions in the cylinder and the higher pressure injection. So it doesn't matter. Now you look at the composition. Paraffin, there are two different diesel fuel composition presented here. One is European diesel fuel, other one is US, American diesel fuel. I have shown these two variants because of the difference in the crude oil reserve. I previously commented about the variation in the crude oil from different parts of the world. So this is a typical European diesel and US diesel. They have a significantly different composition because the crude oil source itself is having a variable, significantly variable composition. That's why the final diesel that you get from refinery also has a variable composition. Okay, so in a European diesel fuel, the aromatic content is only 1.8%. Whereas in American diesel fuel, you see that the aromatic content is very high, 32.4%. And we already know that aromatics are having poor ignition quality, right? This is what we discuss here. It's having poor ignition quality. But American diesel fuel has a very high aromatic content. So what will happen to the cetane number?
It will be 0. Overall number will be less.
It's not only aromatic, you have other paraffin also is there, right? So here paraffin refers to normal paraffin, isoparaffin and cycloparaffin. All this put together is indicated as paraffin. Out of this, normal paraffin is a major component present.
Yeah. So US diesel will be better.
Diesel has a cetane number of around 40. European diesel has a cetane number of around 55. You see a large difference in the cetane number of diesel in different parts of the world. European diesel has a very high cetane number because it has a very low aromatic content. US diesel has a very low cetane. It's a lower limit according to the fuel specification. 40 is a lower limit. It is very low because it has a very high aromatic content. So I have done interesting work for Ford Motors Detroit. You know, Detroit is automotive hub. So Ford wanted to see whether their engine can accommodate diesel with such a significant variation in cetane number. So I've done some work for them and given suggestions for how to optimize engine conditions because the fuel used is having a significantly different ignition quality. In one case it is 55, the other case it is around 40. Okay, but the takeaway for you is in diesel, the normal paraffin content should be increased. Right, because you need fuel with a high reactivity. This is one of the fundamental requirement. You need fuel with a high reactivity for CI engine application. Otherwise, the fuel won't ignite. It may lead to knocking combustion. You need high reactivity fuel. Volatility doesn't matter because you are introducing fuel under favorable condition that helps in vaporizing the fuel. Okay, so now the question to you is, if you know that if you increase aromatic, the cetane number is going to drop, then why US diesel has such a high aromatic? Can anyone tell me? I will stop in another 1 minute. It's already time up. I will take another 1 or 2 minutes and close. Why such a high aromatic content is present in US diesel?
To reduce the noise levels?
No, it will increase the noise level because the delay time is going to be more. Now, what I am asking is, why can't the refineries present in US reduce the aromatic content so that cetane number will be increased?
Sir, is it emissions?
Emissions are also going to be high. Combustion noise is going to be high. Those are the limitations of having high aromatic in diesel. But even then,
maybe it's temperature conditions.
Temperature conditions.
Climate, yes, climate conditions.
Climate condition.
The source of crude oil again is playing.
Exactly, perfect. Source of crude oil plays a role here. The US diesel crude oil has a very high aromatic. So, you know, refinery, there is a cost involved, right? When they refine the fuel, there is associated cost. The source fuel, source crude oil is having high aromatic. So they leave it at such a high level of aromatic, although they know that there is a shortcoming of lower cetane. Although they know it, they cannot reduce it further because there is associated cost. This is a cost intensive, energy intensive process. Refinery process are cost intensive and energy intensive. So if they have to bring it down further, there is a high cost involved, refinery cost involved. They don't want to do that. They have leave it at that. The engine technology should take care of such a poor quality fuel. How do we take care? You have to increase compression ratio. You have to increase injection pressure because you have a fuel with such a poor ignition quality. That is taken care by engine technology. So refineries refine fuel based on the source crude oil. There is associated cost and leave the rest to the engine technology. So the engine technology should be matured enough or advanced enough to take care of using such a poor quality fuel. Meaning The engine and engine OEM and refinery or oil people will go, they discuss and fix the fuel specifications because there is a cost involved in both the case. Okay. With this, I close today's class.
Will sir turbocharger help in what I mean to say, compensate the degradation fuel in that way? Because
Yes, to some extent, turbocharger is increasing pressure,
Combustion issue.
initial pressure and temperature. That will also help in overcoming the poor ignition quality.
okay.
Sir, one doubt, sir. In case of lower temperature regions, if the fuel quality is low, then chances of white smoke will be higher, or how it is?
It will be high. Higher aromatic will lead to high particulate emission. Later on in the second module, I will show how this affects aromatic, how the aromatic content affects smoke formation, but it's going to be high because this is our one major soot precursor. We call it as a precursor. It forms more soot precursor so that the final smoke levels are going to be increased.
Okay, sir. So initially, sir, means the beginning of the combustion, how they counter this to keep it in the level?
No, you have to first ignite, right? To ignite diesel with such a lower CTN number, what you have to do is you have to increase compression ratio.
Yes.
To increase the pressure and temperature in the cylinder at the time of fuel injection. Second one, you have to use high injection pressure. These two will have a significant effect on delay time, ignition delay time. Because your fuel has a poor ignition quality, right? It's a lower bound, 40. So that should be taken care by external conditions.
Sir, but once it is ignited, once the engine is running, it will warm the engine. So the conditions will change, but starting of the ignition, the conditions will be worse. So that difference, how it is taken care in the beginning, sir. That's what I mean to understand, sir.
That's why starting it's a major challenge. Once the engine reaches warm up, it doesn't pose a significant challenge, but starting is a significant challenge. It should be taken care by high compression ratio and high injection pressure, as I said, and they generally also use some intake system because the surrounding weather conditions are also not favorable. You know that, right? In Western countries, the surrounding temperature is very low, so they have an intake heating system also in place.
Okay, sir. Understood, sir. Thank you, sir.
Fine, thank you. So if there are no questions, I will close here. I'll meet you tomorrow.
Thank you, sir.
At 6 o'clock. Thank you.
Thank you, sir.
Bye.
Thanks a lot, sir.
Thank you, sir. Thank you. Bye.